And our next speaker is Tapani Rienen from Emberion. So the stage is yours. Big green one.
Yeah, thank you for introduction, and it is really great to be here presenting a company, Emberion, our technology, our products, but also talking about the new approach to shortwave infrared technologies based on colloidal quantum dots, what are coming as one challenger in concrete and beyond what Emberion is presenting here. So please visit some other companies here. So they have also good stories to tell about what is the relevance of this new technology. Okay, Emberion is a company that produces visible to sphere range cameras. So we have a very broad wavelength range what we cover with our core product. And when we talk about sphere, so we talk about extended sphere range. So we can operate from 400 nanometers to 2000 nanometers. So that so it's a very broad wavelength range. So we fabricate and manufacture our image sensors ourselves, and we have then camera products what provide very affordable concept for when sphere range imaging becomes of interest. We operate at two different sites. We have a manufacturing site, fab site in Cambridge in UK, and we have then camera technology team in Finland in Espoo. So we work from materials to ROIC design to electronics design, software design, and we produce our cameras in our own facilities. We are established 2016 as a spin-out from Nokia's R&D, and currently a little bit less than 40 people working in these two sites, as I mentioned. Okay, let's go now to the interesting part of the talk. So, first of all, starting from here, so that we have here comparison of different pictures taken under exactly the same light conditions using one of the best in-gas cameras from a well-known manufacturer. Similar 20 by 20 micrometer pixels in both two cameras, using the same COVA lens, what covers from 450 to 2000 nanometers. And you can see few features in these images. So first of all, so that what we can create with this technology, we can create very high dynamic range. So that if you look at the image, so the bright areas of the image are not saturated, so that you have gray tones there. But on the other hand, when you look at the dark areas of the image, so we have much better high signal to noise ratio there. I would like to still maybe emphasize here that that we have not as high quantum efficiency in the colloidal quantum dot technologies like in gas, but we can benefit of some other features in this nice way. And one key reason why we get this response is related to the thing that we use measurement mode what gives logarithmic response from the device what enable this very large dynamic range. Okay, so what is our product? What you can find in hall 10 in our booth. That is a industrial camera that is designed to give this spectral range from 400 to 2000 nanometers. we have a capability to go to high frame rates up to 400 frames per second. And this key thing, what I was already saying, that the device enable this very large dynamic range, what there is of interest in, for example, different type of optical power measurements, what are of interest in several industrial applications. Camera has global shutter. We have C-mount for the system, so that they're easy to fix to different type of spectrograms or lenses, and we provide both Kiki and camera link version of the camera. So a little bit then about the solution what we have here, so that the technology is based on two key things. So that first of all, that we have a colloidal quantum dot photodiode structure that is built monolithically on top of a CMOS wafer. So we can start from very standard CMOS process. Built the intelligence into the CMOS process, and then layer by layer develop the photodiode structure on top directly on top of the CMOS structure. So no need for building the device from different substrates. So just starting from the fully processed CMOS wafer and building these additional structures on top of it. Second element of the solution is then related to the way how we have created the electronics, so we can play with the measurement mode, so that they're modes using open circuit voltage or reverse biased mode, what enable this type of a very broad wavelength, broad dynamic range, or large dynamic range for the sensor. Maybe a couple of kind of advantages of a colloidal quantum dot technology as in general. So first of all, so that we are able to very easily now design what is the size or the shape or of the pixel, so that we have full kind of a capability to do the CMOS design. We can have different shapes of the pixels, different size of the pixels, and we can go to very small pixel size if we want to. And that is naturally then limited about if we want to have certain noise performance or some speed for the device, but we can go to very small pixel size if possible, if that is required. Second thing related to colloidal quantum dots, that we can play quite much with the spectral response, so that their selection of the materials, what size of the colloidal quantum dots we use, and how we build the stack, so enable us to tailor the spectral response, so that we can, for example, the devices what you can see in our booth, they are optimized for 1850 nanometer spectral response, so that we can get to this 2000 nanometer wavelength range. But we can also tailor the materials if this is the customer demand to wavelength, that they enable, for example, optimal measurements at 1700 nanometers, for example, for sorting of plastics or applications like that. And finally, all what we do can be done in a wafer scale. So we are all the processing of the devices happen in a wafer scale, and just using a scalable thin film and solution processed layers, so that there's nothing there what requires some specific instrumentation or operation. So we can base the scalability of manufacturing to something what is already there in a semiconductor industry. Okay, a little bit about still kind of a performance figures of our image sensors here. So as said, so that they are based on our own design and on our own readout IC design, so that we have complete control of the technology in this sense. So now we are working for the next generation of devices what go to 1.3 megapixel range and more or less maybe a couple of things from here, so that when operating the device in the normal charge integrating mode or CTIA architecture mode, so that we achieve a good noise level, quantum efficiency of colloidal quantum dot technologies remain below in-gas technologies quite clearly, but on the other hand, we have a relatively good dark current for the devices, but that in this sense the noise performance is still good and sufficient for most of the applications. Then we have this other measurement mode what enable then going to this very large dynamic range. Okay, a few examples of how we can use this technology and what are the kind of interesting things, so that naturally we enable a lot of different applications in hyperspectral sensing and multispectral sensing, what was discussed by previous presenters here, so that there's a lot of different very complex applications there. But there are also many this type of small application areas, like for example packaging inspection in pharmaceutical industry. You need to be able to just check that if things are perfectly kind of filled inside your package. So simple application like that. Then there are another application kind of example here of surveillance in adverse weather conditions. So you are able to see in this wavelength range through fog, through rain, through smoke, like in this particle picture, where our sales team is in some team building event here, so that you can come and visit. You can find some of these people in our booth as well. Okay, but then I would like to kind of maybe give a second kind of idea about what we can do a little bit beyond the typical sphere applications, and that is related to the thing that we can go to 20 nanometer water absorption line. So this is a very interesting application, and that actually opens a lot of different applications. You can see here that when you look at the water droplet in a paper from visible to 1450 nanometer wavelength, and then to 1920 nanometer water absorption peak. So you can see that the contrast of the image is increasing a lot, so that the peak in 1920 nanometers is extremely much significant than in 1450. And this type of application, so that what we can demonstrate, they are really potential for machine vision, optical shorting, different type of applications. And this is something what you can see in our booth, so please come and have a look, so that we have a demonstrator of this working there. You can see it and you can test it yourselves. And maybe then going to just conclusions here, and in a way we are Emberion. We are producing high-performance industrial cameras based on our own monolithic CMOS integrated image sensors, and this is done by combination of different nanomaterials in this photodiode stack. We are also then capable of doing integrated circuit design and camera sensor design so that we are able to optimize the measurement principles to these new materials and take the best out of them. And finally, then this core of the specification of a device. So very broad wavelength range from 400 to 2000 nanometers with low noise, up to 120 dp dynamic range, up to 400 frames per second measurement speed. Thank you very much.
Thank you very much for the nice presentation. The room's now open for question. What we saw was broad spectral range with to sphere camera with what we saw in the pictures, very high resolution. So hopefully there are a lot of questions. So feel free to ask. They are still impressed by the image quality you've shown over this broad spectral range.
Yeah.
No questions? There's a question, please.
Could you just specify a little bit more about this example about the coffee bean? What exactly was the advantage and how did you process it?
Okay, so actually this coffee bean example was just to show that there's naturally quite a lot what you can as such get from different sphere wavelengths, but the core thing was there so that there were water droplets, what was clearly seen as very dark spots in the image. So unfortunately I can't go back to
Was this an actual industrial application or just
that is actual, these are actual industrial applications what we are looking at, especially in the food processing industry, so that what are the key things what can be done there, and naturally water content is quite interesting parameter.
Other application in agriculture?
Agriculture, there's also paper industry. There's a lot of different application areas where there are measurements of water content. So it's quite ubiquitous in different industrial applications.
Thank you.
Okay, thank you very much. There's still room for one more question. Yep, please.
A really simple one. Any plans for a line scan version soon?
Sorry?
Any plans for a line scan camera?
Well, we have actually some work going on in this type of design, that there maybe not line scan, but we are working on devices what would be optimal for push broom type of hyperspectral devices, so that they're in this sense having large high resolution in spatial dimension, having then a little bit less resolution in the spectral sense, but in this way enabling very high measurement of frame rate. So we are working on this type of concept. So please, if you are interested in, so come and visit us in our booth. We can tell more.
Okay, that's it. Thank you very much.